join me in welcoming Alan Samuels, who is a software architect, systems and software solutions from SanDisk.
Well, thank you all for having me.
You want to run?
Well, no, okay, whatever.
Maybe. Oh, this is working.
It's working. Oh, excellent. Yes, I got this guy. Okay, excellent. So, before I came over here, I set up two different presentations that I was going to do, one for the technical track and one for the business track. And when I was on the plane, I got informed that you got one slot to do them. And then when I landed, I made a brief transit through the local medical system here. So I had no time to update the slides. So what I did was I slammed the two together. So what we're going to have is about 15 minutes of what I hope you'll find is interesting technology, and then followed by a product pitch. And so let me start by saying that there's a bunch of lawyer stuff. You can read that later. So what do I mean by infinite bandwidth? Well, I was sitting down with my hardware guy the other day, and we decided to go and plot the speeds of the fundamental components. Because, you know, if software is becoming everything, at the end of the day, you're still left with the hardware. And the hardware dictates what the software is going to be capable of doing. So it's important to understand how the hardware is going to evolve. And that's really what this talk is about. What are the consequences of that? So if you plot the speeds over time for the network, SSDs, and on the bottom line here, what I have is the DRAM bandwidth into a single socket for a CPU in a server, a Xeon class server. And you know, they all have these wonderful, nice learning curves that are all derivative off of Moore's law, except if you look very carefully, you'll notice two of them have about the same slope, and the DRAM one doesn't. Okay. I cheated a little bit here because the top two are in megabytes a second and the bottom one's in gigabytes per second. But the biggest issue is this is a log graph. So if I replot this data for the log impaired, you can see that there's a huge gap that's occurring in the rate of evolution of SSDs and network bandwidth relative to the speed that the CPU is able to provide bandwidth. And that's mostly what I'm going to talk about, is that differential. What are the consequences of that? And what I basically mean is storage bandwidth is becoming effectively infinite. So what I did was, let's turn that data on its head, and let's say, if I have a CPU socket, how many SSDs worth of bandwidth can I support? And the data is a little noisy here in the beginning, but you have a pretty clear trend starting about the time that SSDs really mattered to all of us in the early part of the last decade. And the trend is getting pretty low, but the scale here doesn't look too scary. It looks like, oh, that's nice. Gee, I might be down to maybe 10 SSDs per CPU socket. That sounds pretty good. Trouble is, you actually want to do other things with that bandwidth in the CPU socket, like run your CPU, okay? So a typical Xeon class storage server doesn't run its memory at more than about 20% duty cycle. If the bandwidth, or if the duty cycle of the memory starts to go above 20%, your CPU performance starts to drop off dramatically. Because at the end of the day, it's a von Neumann machine, and it's the latency to memory that matters. So now if you scale that number back in, graph has the same picture, but the Y scale is different. You can now start to see that we're pretty soon getting into some pretty small numbers. What that means is, in another couple of years, you're basically going to be wrapping around every SSD you buy a Xeon CPU. Now, I'm not an Intel shareholder. I work for SanDisk. This is not a future that any of my management or shareholders would like to see. Probably most of you all wouldn't like that either. So that's really the fundamental consequence. Now let's look about how we're going to deal with that. So really, what happens when we get close to that limit? I think I got screensavered. Oh, okay, cool. Ah, there we go. I think I just found a bug in PowerPoint. Okay. Anyways, the first thing they do is what the industry always does when you get close to a problem is you put a Band-Aid on it. Okay. And a standard server that's got maybe 12 slots in it, if you're only going to populate 1 or 2 slots, there's going to be a lot of white space in that server. So the easiest and obvious thing to do is to change the form factors. So you've seen a lot of systems that have blades or sleds or things of that nature, basically new form factors to replace the standard 1 or 2U server. Those are all good short-term solutions to the problem. You know, if you're packing 1 or 2 or 3 SSDs per CPU, these will be good, but they're only going to be a short-term Band-Aid. So what you really got to do is you have to look at the fundamentals and recognize that the cost of the storage today is the cost of the media, plus the access to the media, plus the management of the media. And why do I have to put those together? It's because of the shared nothing storage architecture that people are using. If you take a standard server and you load it up with storage and then run your storage management software on that, you require that all the storage be accessed through the CPU, and you're right back into the same problem. And what it means over time, you can see from the graph, is your storage management costs are going to be dominated by the management, and the storage itself will essentially become free. And that's not what Simon over here wants, or any of my shareholders want. And probably not what you want either, because what it really means is it quits getting cheaper because you're stuck paying your CPU bills. So how do you really get around the problem? Well, you have to embrace the problem. You can't avoid it. Okay? And what does that mean? Well, it means that I want to do my management in software. Software-defined storage. What does that mean? It means that your storage management software is software. It should be treated as software, not as infrastructure. And how do I want to get to the media at the end of the day? Well, I want something that's simple that can be done in hardware. I can't have a CPU in the way, or I'm right back into the pudding. Still want to be able to get to my storage from pretty much everywhere over a network. And I want it to have the same characteristics that I do today, which is the storage should be shareable. It doesn't have to be fine-grained shareable. I don't have to share, kilobyte blocks, but it's got to have some degree of sharing, because storage comes in big chunks that are getting bigger, and our usage of them wants to be smaller than that. I think I see some grinning faces out there that know where I'm headed with this, because we've seen this before, okay? What you really want is a SAN, okay? Or what, since we can't have an old name doing a new thing, we're going to call it fabric-connected storage. Everything old is new again. It's not really your father's SAN, though. SAN, as we know it today, has a number of problems that all want to get fixed. Mostly the problem is Fibre Channel itself. It's pretty brittle. People that have deployed it, we put a lot of Band-Aids on it, but it's just hard to use. SCSI itself is slow. It's got a lot of interesting old stuff that no longer matters that ends up slowing it up. And we need something that does subdrive storage allocation. The good news is a lot of this is actually already being worked on in the industry today. Some of you may be familiar with NVMe or NVMe over fabrics. That's development work that's going on in the storage world today. And it really has most of the characteristics that we're looking for. The 1.0 spec is out for review. I think it's supposed to be done this month. It's simple enough. We're going to be able to do it in hardware. You're not going to need a CPU to be a target for NVMe over fabrics, at least not in the long term. Hold that thought. I'm going to come back to it. Most of the performance that you get out of NVMe drives doesn't come from the hardware. It comes from the fact that the drive is so much simpler to talk to that you're not going through the legacy SCSI stack. That's where the huge improvements in latency are that you're getting in NVMe drives. And the new namespaces stuff gives you the subdrive allocation. The only real problem is it's just not really ready for enterprise deployment yet. But what about the network? I said Fibre Channel doesn't do it. It's too brittle. We all know that over the long haul, the economics that you want are Ethernet. That's what everybody wants. We really want one network to rule it all. Problem is, aren't quite there yet. there's really two competing protocols for moving storage over Ethernet today. You've got Rocky and iWarp. And both of them sort of solve half the problem. You can sort of take your poison. You can make your edge nodes easy to do, which is what Mellanox has done with Rocky. That pushes a lot of the problem into the network. It's not really clear if that's a solvable problem. I haven't seen any large-scale deployments that tell me that it has been solved. All the vendors tell me that it's been solved, but I'll sort of believe it when I see it. Or you can go with iWarp. We know the network problems with iWarp aren't a problem, but building iWarp edge nodes seems to be difficult. Been several attempts on the part of many vendors, and then they failed. It may be too difficult on a general case. So you're really not going to see storage over IP until this thing plays itself out, and stay tuned. So what's that going to look like? Well, the first generation of the next, we'll build it with off-the-shelf stuff. That's what we always do in the industry. Take the old server, slap some SSDs and a NIC into it, write some software, and you've got a product. I'm aware of several startups that are bringing these kind of products to market. We've seen some prototypes at various shows, getting 4 to 5 million IOPS with some big CPUs and big SSDs. Seems like it ought to be able to get to 10 without, really stressing anything. I think that's what you're going to see in the first generation. But fundamentally, you haven't solved the problem. You basically turned your CPU into a giant DMA controller. So the next generation of this is we're going to get the CPU out of the path. And there are a number of NIC vendors that are working on this code already. Some of you are probably up on that. But what you do here is teach your NIC to crack the commands that come in. I said they're simple enough to be executed in hardware, so even my NIC can do it, and send those directly to the SSD. The problem is, while the commands aren't flowing through the CPU, the data is still flowing through the CPU. So you haven't solved the bottleneck. However, you've gotten back a lot of CPU performance, and that's a really good thing. People are going to like that. We're going to see a lot of that out there in this world. I think the vendors of those products will do quite well. We're getting even closer to the wall. So finally, what does it take to get past this? Well, I think the answer is that we're going to see a follow-on generation of products that basically rethink the interface completely and get the DRAM out of it entirely. We'll bring Ethernet directly into the SSDs. There won't be any buffering in the way. There won't be any CPUs in the way. And this works really well with rack scale architecture. What do I mean by that? Well, that's how we're going to get really small. So in a rack scale architecture, some of you may have seen some of the presentations from Intel, some of the other companies that are pushing this. What you really do is you gather up, it's sort of like the rack reimagined. Take your rack of equipment, throw all the parts on the floor, gather up all the CPUs into one place, gather up all the storage in one place, gather up all the NICs in one place, and connect them with a local fabric that's high speed. And now, the real advantage is that you can vary the amount of compute and storage and networking independently of each other. Essentially, the largest problem that we've got with the shared nothing architecture is because the CPU is in the way and it is the fundamental bottleneck to what's going on, you have to choose the amount of CPU versus storage right when you provision your racks at the beginning of the day. And that's going to limit the variability of your deployed infrastructure on top of it. In other words, if you think about it in the OpenStack context, what I really want is a hardware substrate that I can pour my software personality into. And whether that personality is, say, block devices on Ceph, or MongoDB, or some other storage infrastructure software, what you're going to find is that the ratio of compute to storage is going to vary dramatically for those applications, and it's going to be very hard to build your hardware to match that with a conventional architecture. The way you get around that problem is with the rack scale architecture, which I think you're going to increasingly start to see. So my call to action for people in the community is to really start to think about this as a way that people are going to want to be building their hardware infrastructures to make them more generic and more software driven. And we don't really have the right kind of management. You know, if you go look at OpenStack today, we've got very good management at the top. Things like Cinder and Manila and Swift give you very good ability to manage things above the storage management layer, but you're completely left with essentially no help at all in implementing the storage management layer. Okay, and you know, that's a pretty big challenge for a lot of people. So we're really going to want to take the storage management problem, which itself is a pretty complicated problem, and move that more into the automation domain that you get with OpenStack. And in order to do that, you're going to need to be able to manage the hardware at a lower layer, and you're going to have to provide a more regular distribution of the hardware. So what does it all mean? You know, it's pretty much a summation of what I said. Don't stick your storage, don't imprison it behind a CPU. It wants to be free. And rack scale architecture is in your future, and that's really where software-defined things actually make sense. So that was my first talk, okay? So now I'll give you a product pitch. I think I still got a little bit of time, okay? 10 minutes, okay, excellent, okay. That should be about right, okay? So come on by the booth, you'll get to see the box, but basically the story is that SanDisk is creating a new model of software-defined all-flash storage. We have a product that is right, here's a good picture of the product. It's 0.5 petabyte of flash in a 3U chassis, no compute. It's the beginnings of the rack scale architecture that I talked about in the previous process. It's got 8 SAS links, because SAS is the only really workable storage fabric right now, except unless you want to go Fibre Channel, et cetera. We talked about that earlier. We're on the second version of this product now. It gets about 2 million IOPS with about a 1 to 2 millisecond latency on that. About 12 to 15 gigabytes per second. And the variability on that is just how quickly you can schedule things and what are the sizes of the operations, et cetera. Okay. It's an enterprise class device. Basically everything is hot swappable. It's all managed in band with Ceph commands to it. And essentially it looks like 64 8 terabyte SSDs. And if you plug in your SAS link, you don't do any of the zoning, that's exactly what will show up on Linux. 64 devices and you're off to the races. You can put any kind of software on that you want. We actually have alliances with a number of companies that range from GPFS to Nexenta, Tegile, Scaleout. There's a longer list. See the SanDisk guys down in the booth. I personally spend a lot of energy working on Ceph. SanDisk has been a big contributor to Ceph from the early days, long before Red Hot bought them. If you look back historically at Ceph, you've seen about a 1.5 orders of magnitude performance improvement on it, and that's mostly due to the work that my team has been doing together with the ink tank people. And there's more to come. There's actually quite a bit more performance in Ceph that'll be coming in the K and the L release, as well as all the other good stuff about Ceph. That it's really got all the enterprise class storage features that you need for managing large scale data deployments. You know, if you're only going to want to put up 1 or 2 boxes, Ceph is probably overkill for that. But if you're managing a data center of 100 or 1,000, then this is exactly the kind of tool that you want. Let's see. SanDisk itself, we offer a version of Ceph. It's essentially the code is the same as the mainstream. It's not a fork of the product. Okay, it's completely interoperable with the community version. But what we do is we provide tuning parameters that get you considerably increment in performance over what you'll get with off-the-shelf Ceph. You know, this is really something you see with all the software-defined storage products, which is they'll all work on the hardware, but they usually don't work well until you get in and tune them. And getting these products tuned up for your hardware plant often makes a 2, 3, or a 4x difference in the performance. That translates right into money. on the bottom line. And you got to figure out, are you going to be on the hook to do that yourself, or are you going to get that from somebody with a vested interest? With Ceph and SanDisk, we'll do that for you for a little bit of money. Ceph is a scale-out product. You can really scale it horizontally, independent of any kind of workload. You can get hundreds of millions of IOPS out of Ceph. Just keep deploying hardware. One of the really nice things about scale-out products as opposed to scale-up products is you don't care so much about the performance, you care about the price performance. And that's really a shift that it takes a while to wrap your head around it, because in a scale-out product, you can get to any performance level you want simply by continuing to scale it out. So what matters is how efficiently you scale from 100,000 to 1 million to 10 million, et cetera. And we think that this kind of scale-out architecture is really the future and is exactly what you're going to be wanting to do in large-scale OpenStack deployments. It's the only thing that's going to really let you self-manage things at that scale. So the product that we offer, in addition to the community distribution, we've got the tunings that I talked about. We have an installer for it. It's also integrated into the management console so that you can get in and interrogate the hardware and get stats out of the hardware and turn on the blinking lights and all that good stuff, okay, when you need it. And this slide's a little old. We're showing 900K IOPS. This is into 384 terabytes of storage. If you max the box out at 512, you can get over 1 million. We should update this slide. I'm sorry. Okay, I'm my fault. Sorry.
We can get over 2 million IOPS, but that'll
right.
be under 2 milliseconds.
Right. Okay. Right. So and this is random 4K reads. And more stuff. Lots of numbers. Somebody's going to take a picture of it. I'll let them do that. Okay. I can't imagine you want me to walk through all these numbers. It's all goodness and light. More speed than you can really need. Here, now, come on. Next picture. The key thing is we're getting about 80% of the bare metal performance out of Ceph right now. So Ceph itself is putting about a 20% tax on what's going on, which for Ceph, that's actually pretty good. I think we'll see that gap will continue to close in the subsequent releases that are coming. And the last thing that we do at SanDisk is testing, lots of it. One of the things about software-defined storage is your software-defined storage vendor, he writes things to an API and an illusion of how the hardware is supposed to work. And it will work on the hardware he tests it on, but it might not work on somebody else's hardware. We've all run into those kinds of problems. Well, that's part of the problem that we own, making sure that the product actually survives on our hardware. And it's not just debugging the hardware itself. Of course, we're responsible for that. It's not just debugging the software itself. We share that responsibility with the Ceph community. But it's making sure that when you put the two of those together, that it actually works. Okay? So things like we do lots of power, crash testing, power off testing, kind of mundane stuff. Okay? We've invested quite a bit into that area. One more picture. Okay. He's getting bored with me already. Anyways, this gives you an idea of the kinds of systems that you can build. And they're essentially off-the-shelf servers today with Ceph. At the kind of performance levels that you can get from InfiniFlash, you can stick up to 8 servers in front of that, and that will allow you to get to fully utilize the hardware even at its smallest block size. And the last thing, Flash isn't as expensive as you think it is. That's the thing. Yes, I'm getting the 2-minute sign. Okay. Essentially, the standard cost models for storage need to be updated to handle Flash in at least 2 different dimensions. One is power consumption, And over a multi-year period, that'll matter a lot. The other is redundancy. If you're assuming that you're going to take flash and triple replicate the flash just like you do with your HDD, you're going to have so much durability that you've been wasting money on it. And the reason is that flash is dramatically more reliable. I have a whole other presentation on that, which I'm out of time for. But what's important to realize is that something like, even as simple as 2 copies of the data on flash is way more reliable than 3 copies of the data on HDD. So that all rolls up into it being cheaper over, it does cost more to acquire flash, but operationally over time, it can be superior. Thank you.